All right, and we're back to some more elementary statistics. Welcome to the second video of the enrichment content course thing. Now we're going to be working with exploring and organizing data. So once we collect our data, we have to do some stuff to it. We need to analyze it and we need to present it so that other people can also take a look at it and understand what is actually going on. So that is what we'll be covering in this video. So we'll be covering three major kind of points here. The first one is frequency distributions. It's one of the main ways that data can be presented, followed by histograms. It's also a really nice type of graph that is used a lot in statistics. It's a really cool one. And we'll finish off with a couple of good graphs versus bad graphs. I'll show you some acceptable graphs that are used a lot in statistical research. And then I'll show you two examples of bad graphs and stuff you should avoid if you are to present your data. Okay, so let's go. The very first main topic here, frequency distributions. First of all, what is a frequency distribution? It can also be called a frequency table. This table shows how data is organized into different categories that we call classes. And next to the classes, we're gonna write how many frequencies or how many times a certain value falls into that class. In other words, we're keeping tally marks of how many values fall into our specific classes. It sounds a little weird once you are verbally saying it, but later on we're actually going to do an example on this, so you'll be able to see what I mean by classes and the ranges and frequencies and whatnot. But this is just like the official definition for it. We will be working with frequency distributions in the next video as well, so make a note of this. This is a pretty important one. Now, here's the thing with frequency tables. This is the steps you need to take to create one from scratch. So if you just have a data set, just a set of a lot of different values, this is what you need to do to create a full-on frequency table. Some professors do cover this process. They do it just step by step, and it's also gone over in class, right? They go over the entire process. But in the homework and in the quizzes and in the tests, they never have students making one from scratch. They skip the first 5 steps and they just start at the 6th one. So I'm not sure why they go through the trouble of showing all the steps when they always skip the first 5. So what I'll be doing in our example that we'll be trying out, I will also be skipping the first 5 steps because there's no point in showing this if you're not actually going to do it. So that's that, okay? Now, here we go. The following data are the survival lengths in months of 48 patients from the start of their treatment until their deaths. So this is a very gruesome data set, right? But this is commonly used in the medical field or in the pharmaceutical field. A company wants to test out if their drug is actually useful, if it's actually working. So they will try and test this drug or treatment on patients and keep track of how effective it is. So even though it is a little gruesome, it's just something that is measured in the real life, in real research. So the instructions for this problem is to construct a frequency table. So like I mentioned before, we're gonna skip the first 5 steps. We're not gonna go through getting the class width and the lower class limit and all that stuff. This is most likely what you're gonna see. So on the left column, we have the classes. So survival length in months. And then the first class is 0 to 6. So 0 months to 6 months. Next class is 7 to 13. And all the other classes are already done for us. All we need to do is take a look at our data and count how many times a value fits in each class. So for example, the first class, 0 to 6, let's take a look at our data and see how many values fall within that range. So I can see that the very first one here, the 3, falls between 0 and 6. So does that 5. And also that 2 over there on the right. And that's it. No more values fall between 0 to 6. So that class has a frequency of 3. Because 3 values fall within that range. We move on to the next one, 7 to 13. Right there near the beginning, 11 falls within 7 to 13. And so does that 12 and the 13. And that's it. No more values fall between 7 to 13. So that class has a frequency of 3 as well. So obviously we keep doing this for all the other classes until our frequency table is complete. This is going to take a while. It does require some patience to go through each single individual data value and then marking them out and putting it in the frequency table. So take it slow. Don't try to rush it, because we may end up making a mistake and then the rest of our research is going to be incorrect. And there it is. That is our frequency table. Pretty neat, huh? So now here, just to reiterate what we're doing here, we organized our data into different classes. So that first class, 0 to 6, that means that only 3 AIDS patients survived anywhere between 0 to 6 months. It's the second class, also only 3 AIDS patients survived 7 to 13 months. So that's essentially what we did. We organized just these values into a little chart that we can easily read. And there we go. Cool stuff. However, there's even more that we can do with the frequency table. We can do a little more cool stuff here. Oh yes, don't forget to make a note on a frequency table, because we will be seeing it again in the next video. Aside from a normal frequency distribution, we also have a relative frequency distribution, also known as a percentage frequency distribution. So now here, instead of frequencies that we're keeping track now of the relative frequency, also called a proportion, also called a percentage, hence the percent sign on the right here. So how do we get a relative frequency for a class? Well, we add up all the frequencies and then we just divide the frequency for that specific class by the total. And if you want a percentage, you just multiply by 100%. So let's actually do that with our frequency table that we just found. So like we mentioned before, we need some totals. So the very first thing is we're going to add up all our frequencies. The 3, the 3, the 10, the 11, 8, 3, and 2. If we add them all up, we get a 40. And this was already known to us since the beginning. The problem told us that we had 48 patients. So the frequencies should add up to 40. So now what we're going to do, we're going to go class by class and divide its respective frequency by the total value of frequencies we have. So the very first class there, we're going to get a 3 divided by a 40. And that gives us a 0.075. Also, you can write it as a percentage by multiplying by 100%. So you get a 7.5%. You can use any of these. You can use the fractions or the decimals or the percents. Decimals and percents are a little more useful here, so I'd recommend using either of those two. I prefer the decimals, but I'll include all three just for this example. Okay. The next class is also a 3, so it's gonna be the exact same thing. 0.075 or 7.5%. The third class is 10 divided by 40, which is a quarter, 0.25 or 25%. So we do the exact same thing for the rest of the classes in our frequency table. And then we're gonna find all of the relative frequencies. Now, if we want to check our work here, we can also add up all the relative frequencies, and we should get something close to 1, or exactly 1. So we add up all the relative frequencies, we get 40 divided by 40, which is equal to 1, which is also equal to 100%. It is possible that you may get a relative, like a sum that is a little less than 1 or a little greater than 1. That's okay. We may end up rounding, and once we round, we are gonna get some rounding error within our relative frequencies. So if you add them and you don't get exactly 1 or 100%, don't worry too much about it. There is a little bit of wiggle that we accept. But yeah, and that is our relative frequency. So now we can have a cumulative relative frequency distribution. These titles are getting longer and longer. What we're doing in this frequency table here, we're gonna add each class's respective frequencies to the previous frequencies that we have. Now, what in the world does that mean? Allow me to explain in the next slide. So this is our frequency table, right? It's getting larger and larger. What we're gonna do, we're gonna get each class's relative frequency and add it to the previous one. The very first relative frequency, it doesn't have a relative frequency prior to it. So it's just, since it's the first one, there is no frequency before it. So we're just gonna bring it over. You just copy paste. 0.075. Now is where the fun begins. We're gonna bring that first 0.075 down and add it to the next class's relative frequency, which is also a 0.075. We add those together, we get 0.15. And now we bring that 0.15 down and add it to the next relative frequency, 0.25. And that gives us a 0.4. And then we bring that 0.4 down and add it to the next relative frequency, which gives us a 0.675. And we're going to repeat that same pattern over and over until we get to our very last relative frequency. And the very last sum should be a 1. And just like I mentioned before, it's okay if it's not exactly 1. Could be a little less or a little more. Also, you can choose to add these as their percentages, or you can use the decimals as I did. Up to you. And that is our cumulative relative frequency distribution. And that's about as far as we can go, at least for this class. We aren't going to add more columns or more process to this table. That's as far as we go. Just one more thing to note here. There is a different way that some books write a cumulative relative frequency distribution. For whatever reason, they drop the ranges. So they drop the 0 to 6, for example, and instead they write less than 7. So essentially what we're doing, we're dropping the range and we're just gonna write less than and then the next lower class limit. So the next class, the 7 to 13, We drop it, and it's going to be less than 14. And then we also drop the 14 to 20 to less than 21. And we do the same thing for the rest of the classes here. I'm not entirely sure why they do this, why they would prefer a less than the next lower classes limit. It seems a little weird for me, but I mean, whatever. Whatever your professor is asking for, or whatever your book is asking for, just give it what it wants, and you'll get credit. Okay, so stick to what you see in your class. Just keep in mind there's different ways of writing certain things. And there we go. That's all that we have to do with a frequency distribution. A lot of cool stuff that we can do, right? So now let's move on to our next topic. And as I mentioned in the beginning, histograms are very commonly used to display some data. Histogram is a graph consisting of bars. They have the exact same width, or the same thickness to them, and they're drawn next to each other. So there are no gaps unless there is a gap within the distribution. Then, well, there's nothing we can do. They're just going to be gaps. The horizontal scale here contains numerical data, and the vertical scale contains the frequencies. So a histogram is basically the graph of a frequency table, which is pretty nice. They kind of go hand in hand. There is a different kind of frequency histogram, or a different kind of histogram, I should say, which is a relative frequency histogram. The only difference here, it's almost the exact same thing as a normal histogram, except now the heights, the vertical scale here is measuring the relative frequency instead of just the frequencies. So their percents or their decimals. That's about the only difference between those two. So yeah, pretty neat. Here we go. These are some common distribution shapes found in histograms or just data graphs in general. On the top left, we've got this thing we call a bell-shaped distribution. More oftenly called, or more officially called in statistics, is a normal distribution. So it starts off really low, and it just goes up and up, up, and it peaks at some point, and then it goes down, 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 and just like that. Make a very special note about the normal distribution. We are going to be working with it so much in the future, starting off with, I don't think the next video or the next chapter. Chapter 6 is where we'll be just working non-stop. Chapter 5 we see it as well, but just keep in mind we'll be using this distribution a whole lot. It's really important. On the top right side, we've got a uniform distribution, which kind of makes like a rectangle there. Not a perfect one, but close. This one's also important. Not as important as the normal one, but we will be working with this later on. So make note of these two. And on the bottom, we have skewed distributions. That means that a lot of data is more lumped to one side than the other. And if we talk about it in respect to the lump, it's a little counterintuitive. So for example, skew to the right, the lump is on the left side. The majority of the data is on the left side, yet it's called right skewed. And the bottom right one, we've got skewed to the left, where the majority of the data is on the right. So it's a little counterintuitive to look at it that way. Instead, just follow the tail. So where is the tail in our blue graph here? It's on the right side, right? The majority of the data is on the left, so the tail then falls over to the right. So that's why it's right skewed. Just follow the tail. The tail's on the right, it is right skewed. On the brown graph, the tail is on the left, so then it's left skewed. A skew to the right is also called positive skewed, and skew to the left is called a negative skewed. So that's different ways of calling them as well. But yeah, just follow the tail and you will be okay. Now, we get to some cool stuff. How do we create a histogram? There are two main options. The very first one here is to use a Texas Instruments calculator, or a TI calculator for short. You can use a TI-83 or a TI-84. Now, these calculators are expensive. The one I got cost me 150 bucks. And obviously, not a lot of people are willing to throw that much money into just a calculator, right? So if you're on a tight budget, or you just don't want to spend that much on just a calculator, then I highly suggest you taking a look at StatDisk online. It's a free service that you can use. All you have to do is just register with an email, and you'll be able to use so many tools that are used in stats. Like I mentioned, this is free. You won't have to pay anything. You just sign up with an email. If you don't want to use your personal email for security reasons, just create the new one, a new throwaway email, and you'll be safe. But yeah, these are the two main ways. Obviously, you can do it by hand, but that's gonna take a lot of time, and time is what we least have right now. So I'll go over these two because they are the quickest ones. So, first of all, how about we take a look at creating a histogram with the data that we worked with previously about the AIDS patients and their survival lengths. We bring up our frequency table. This is how it looks like. So, how do we create a histogram with a Texas Instrument calculator? Let's see. Okay, so here we go. Here is the calculator that I got. I'm using emulating software. If you want to use an emulator as well, that will be up to you. You're gonna have to do your own research on an emulator. There are also some apps flying around. I haven't tested them or seen if they're any good. So once again, you're gonna have to do your own research there. But for now, this is a calculator that I decided to use. TI-84 plus C Silver Edition. You can use any iteration. There are many different ones, so they're all gonna work. So, histogram time, right? How do we create a histogram? The very first thing we're gonna need to do in our calculator is to toss all this data into a list. So now, how do we do that? First thing we're gonna do, we're gonna go over here to our stat button. It's right next to the left arrow key. And that takes us to this window. We got different tabs. We got an edit tab, calculate, and a tests one. To work with lists, we go to the edit one, and it's actually option 1, which is also called edit. Now to select it, you can just either press the 1 key or the enter. I'll hit enter. And you're gonna have to input every single data value. You can use any list. I just put it in list 1 because that's the first one. So list 1 will contain all our data values. And as I mentioned, you're gonna have to type in every single one. So just like when creating a frequency table, be patient because there are a lot of data values to go through, especially in this problem. And once you input all the data values, make sure to double check because we may miss a number, and if we continue with missing values or values that are incorrectly written, we're gonna throw all our work down the drain, which is not good. So input and double check always. So once we do that, Now what we need to do is we're gonna hit the second key, which is this little blue button. If you're using a different calculator or an older one, color may be different. Doesn't really matter, just the second key. That's gonna bring up a little arrow up top. And now we're gonna go to stat plot, which is right above this y equals button. Since we have the second key activated, we're gonna go to that second function, which is stat plot. So here we got 3 stat plots that we can have activated. We'll just choose the first one because it's the first one. And we're gonna activate it. We're gonna go to on. And here we have different graphs that we can use. Since we're working with the histogram, we're gonna choose the third one there. That is our histogram. So the X list will be the list that contains all our data values. And we put it in list 1. So we're gonna leave list 1 right there where it is. The frequency, we won't worry about it, just leave it as a 1. The color also doesn't really matter. If you're using a TI-83, that doesn't have any color at all. So yeah, don't worry so much about it, it's just fancy looking. So now that we have this activated, how do we get to our graph? We're gonna go over here to the zoom button. Here we got many different options. You can zoom in, zoom out, but the main one we're gonna use is zoom stat. The calculator is gonna recognize, oh, you wanna display a statistical graph from your stat plot? Okay, I got you. And it's gonna rearrange the window so that we can see it in its entirety. So we choose option 9. And there we go. It just spits out a histogram really quickly. If we hit the trace button, we can actually move around and see how many frequencies our bars have. So here, less than 9, we got 3 values there. We got 6 values, less than 16. And if you notice, these frequencies are different than the ones we have in our frequency table. They're not matching. So how do we fix that? We can go over to the window button and we can fix some of the dimensions here. So if you notice in our frequency table, we start at a 0. So our very first X minimum value, it should be a 0. Our graph also doesn't go up to 51. It stops at 48. So I'm gonna go ahead and change that to 48. And here the X scale, so by how much we're going, we're gonna actually leave it at 7. In our data table here, our frequency table, we're also going by 7. So from 0 to 7, that's 7. From 6 to 13, also 7. So we're just going by 7s. We could also modify the Y values here if you wanted to. I'm gonna put a 0 here. Whoops. There we go. 0. And our highest frequency is an 11. I'll just go up to a 12 so we can see the graph even better. Looks about right. Once we do all that, then we just hit the graph key and it'll take us back to our histogram. Okay, there we go. Looking better. So here, on the less than 7, hey, look at that. It looks like the other way to write the cumulative relative frequency. With the less than 7 thing over here on the max. Cool. That's a pretty nice coincidence there. So we got 3 frequencies there, and then a 3, a 10, 11, 8, a 3, and a 2. So now it's matching our frequency table. And bam, there is our histogram using a Texas Instruments calculator. we go. Now, how do we do this thing on StatDisk? Let me show you. So this right here is StatDisk. You got a lot of things going on: analysis, data sets. Got some lists here. Once you open it, the first list should be empty, but I go ahead and input all the data values there from our problem. So once you do input all the data values, like I mentioned, make sure to, once you input them in, to double check to make sure that all the data values are there, that they're correctly written. So now, once we have the data input, we gotta go to data, and we'll be choosing the histogram, because that's what we want to create, a histogram. So that'll take us to this next window. Here we need to select the column in which we input our data values. I put that in the column number 1. We can actually title our histogram, which is appropriate. So I can call it something like histogram of survival lengths. The G and then the TH sound is so weird. But yeah. The X value, we can also label it. It's measured in months, so probably write down months. Frequency, we can actually just leave it as a frequency for the vertical scale. Now here, we can have StatDisk kind of just create the histogram and adjust it any way it wants. If we do that, it's not gonna match our frequency table, which is not what we want. We want it to match, right? So what we have to do is just click this little dot there, and class width, so how thick our rectangles are. It's basically how by how many values we're going in our class. So we were going by 7ths, so the class width is a 7, and we started with the 0, right? And there we go. So now if we plot this now, look at that. That is our histogram, and it's matching the exact same values from our frequency table. Ain't that pretty neat? Also, you can choose to have a relative frequency instead of just the frequency. So if we choose that, it's gonna switch this over to 7.5. And these should actually have a percent sign after the number, because that's what they're showing here. So this should be a 25%, 27.5%, but it's okay. I can let that slide. And there we go. That's how we create a histogram using either of those two methods. So choose whichever method you want. If a friend or a family member or just anyone has a Texas calculator, ask if you can borrow it, or if you can borrow one from your school, or just if you get your hands on one, it'd be really useful. If not, StatDisk online is a good option. So yeah, there we go. So the last topic for today will be good graphs versus bad graphs. Like I mentioned in the intro, there are some graphs that are commonly used in statistics, that are widely accepted. They are good. But there are some practices that a lot of organizations use to distort the data and present it in a false way, which is not what you want to do with data. You want to be as upfront as possible, you know, just show it off honestly. So here we go. Let's take a look at some good graphs. Here we have a dot plot. So it's a graph of numerical data. Each data value is plotted on a number line. So as we see here, we got a number line going, and right above each of the values, we input, or we just plot a little point there. If there are any repeated values, we just stack them up like that 2 there. It's got 6 dots above it. And if you take a closer look here, this is discrete. If you remember from the last video, they're all whole numbers, and the data values are only on top of the whole numbers. I have seen some dot plots that are continuous, so there are some dots a little less or a little more than just a whole number, so in between those gaps there. The most common and the most simplest, or the simplest dot plot out there is the one that looks like here in the example, just whole numbers. But you could have some continuous ones there. Cool. A scatter plot is similar to a dot plot. However, here the dot plot only had the horizontal axis, whereas a scatter plot adds a vertical axis to it. And the way we graph data value is similar, or actually just the exact same thing as a XY ordered pair from a rectangular coordinate system, if you remember that from algebra. So you just move a little towards the right, and then up, and then you just plot your point, and there you go. And this type of graph is used to display two different variables. For example, here we're measuring height versus weight. So they don't have to be the exact same variable, it could be different. And it's pretty useful. Make a little note about the scatter plot here. We will be working with it in chapter 10. Should be like the 10th video, I'm assuming. And it's actually my favorite chapter. And I can't wait to get to it, because it's going to be awesome. Yeah. The next graph we got is a stem and leaf plot. Or for short, just you can call it a stem plot. This is an interesting one. Here we're breaking off a number into the stem, which is the leftmost digit, and the leaf, which is the rightmost digit. What do we mean by this? Here, the example, we got some values highlighted next to the 4. That 4 there is basically the tens place. So that 4 stands for 40. And the numbers towards the right of it, those count as the ones place. So if you put together the 4 and the 2, then we get a 42. And then the 4 and the 3 will make a 43. And then 44, 46, 48, another 48, and a 49. So it's kind of interesting graph here. We can actually see the distribution of how the shape looks like. Gonna have to tilt our heads a little towards the side in order to see it. But it's a pretty neat graph. I like it. Not as much as a scatter plot and other graphs, but it's got its place. A box and whiskers diagram, also known as a box plot. This is a graph of a special data set known as a 5-number summary. It consists of the minimum value, first quartile, the median, the third quartile, and the maximum data value. Also make a little note about the box plot. We will be seeing this in the next video when we start working with some descriptive statistics and measures of, what was it? Relative standing. That's where we work into the quartiles and stuff. So we'll see that in the next video. A time series graph. This one's pretty cool. It's just numerical data collected at different points in time. The example shows the price of gold in dollars throughout the years. So if you're into the stock market or into precious metals or cryptocurrencies as well, time series graphs are used to show the price of those assets throughout different periods of time. It could be a day, it could be a month, a year, or just all the time that that asset has been in circulation, which is pretty neat. Now here we got a familiar face here, a bar graph. So all the bars have the exact same width, they have the same thickness. But if you take a look at the horizontal axis, that is categorical data. So rabbit, dog, cat, goldfish, and hamster. They're just categories. and the bars are separated by little gaps. So, as we can see, a bar graph is for categorical data. We can't subtract rabbit minus dog or have goldfish divided by hamster. We just can't do anything like that. So this is the main difference between a bar graph and a histogram. So here, the histogram is making a brief reappearance. Histogram, the bars, same width, but there are no gaps. The bars kind of put together. And the data is numerical. So that's the main difference there. Histogram is for numerical, bar graph, categorical. A Pareto chart. It's the exact same thing as a bar graph, except that the bars are now organized from greatest frequencies to lowest. I don't really know why you would want to do that, but I mean, it's a thing. It's also got its place in the statistical graphs. So the more ways you have to organize and display data, the better. You can choose anyone, so you can use a Pareto chart if you want. This one here needs no introduction. I'm pretty sure we've all seen this since way back in elementary school. The pie chart. It just depicts categorical data, once more, as slices of a circle or a pie. And the sizes of those parts here are proportional to how many frequencies that slice has, or relative frequencies. So here this graph is keeping track of how many users there are for different web browsers. Got Firefox, Chrome, Opera, Safari, Internet Explorer. I personally use the Brave browser. I think it's pretty neat. But yeah, pie chart is cool. Last but not least, we got the frequency polygon. Here, this little guy is the exact same thing as a histogram. Except here that it's using dots and lines. You can use either or between a histogram or a frequency polygon. Here they're using the class midpoints, so yeah. I think the frequency polygon looks a little cooler than a histogram, but I don't know. You can use either or. They look pretty neat. Also, the vertical axis could also be a relative frequency. So you could have percentages there if you so wish and desired. Now, let me show you a couple bad graphs. One of the main the main ways that data is distorted is by using a non-zero vertical axis. If you take a look at the graph on the left, the 1998, we got the average house prices there. So got about 80,000 and almost 81,000. And then you go to 1999 and bam, it's a massive increase in prices. Oh my God, houses in America are so expensive. We're gonna burn it all to the ground. No. If you take a look at the right graph there, that is what the data actually looks like. That vertical axis is now starting at 0, and the difference is not that big. So by not using a 0 as your starting point, you can easily manipulate data and exaggerate the differences between groups, which is not good. You don't manipulate data. Show it honestly. That's just how you should do things. Another way that data is distorted with pictographs. Data is usually one-dimensional. It's just the value. But if you depict it with two-dimensional objects or three-dimensional ones, you're gonna distort it really bad. So here we got the United States is producing more trash. So in 1960, we got 80 million tons. It's like, wow, that's a lot of trash. But then you go to 1980 and oh my God, the United States is the worst country. It's producing so much trash, it's gonna kill all life on the world. But no, just slow down and take a look at the graph. In 1960, we got 80 million tons. Then we go over to 1980, that's 20 years in difference, and now we have 160 million tons. It doubled, right? So 80 times 2 is 160. But the picture there, those little trash cans, it looks like you can fit 4 little trash cans into the larger one. So it's making it look like the amount of trash has quadrupled, where it in fact just doubled. It's still a lot of trash, that is true. We're gonna have to clean up after ourselves a lot better, but it's distorting the data. It's making the difference so massively huge. And that is not okay. You don't manipulate the data. Just show it honestly. And the reason why this is shown, a lot of influencers or leaders or organizations, they do this a lot. They're gonna twist the data into their favor to sway your opinion, and so they can push their agenda or to have things done their way or just whatever they're trying to do. They're gonna do this a lot. So it's really important that you are able to identify these, this manipulation, this kind of sketchy looking data, so that way you are not easily swayed. And this is really important. So watch out for pictographs and non-zero vertical axis. And if you're going to present data in any way for whatever reason, just choose one of the good graphs. Those are good. Don't try to be cute with the pictograph. Just don't. Just keep it simple and display the graph and the data honestly. Okay? Okay. I'm leaving that in your hands now. Next week, we'll be now describing and comparing data. We got 3 different measures here. We got center, variation, and relative standing. Making a surprise reappearance, box plots. So look forward to seeing all that fun stuff. Okay, everybody. See you next week.